Right now, the tech industry is planning to build nuclear power plants just to keep up with the energy demands of artificial intelligence. By some estimates, data centers could soon consume up to half of the power output of entire states. And yet, the most sophisticated cognitive engine in the known universe, your brain runs on just 20 watts of power. That's less than a dim, flickering light bulb. How is this possible? For the last 70 years, computer science and neuroscience have shared a foundational belief that the mind is a digital-like telegraph network, a web of billions of individual neurons passing discrete signals across a gazillion synapses. We call this connectionism. It's the very architecture we use to build large language models. But what if this entire model is missing the point? In a recent seminar hosted by developmental biologist Michael Levin, MIT neuroscientist Earl Miller presented a paradigm-shifting alternative. Cognition doesn't emerge from static connections. It emerges from the physics of moving electric fields. The 20th century view of the brain was simple. Sensory inputs come in, they get combined by specialized neurons, like a line detector or a face detector, and eventually we get a thought. But around the turn of the century, neuroscientists made a troubling discovery: multifunctional neurons. In the cortex, a single neuron doesn't just do one thing. If you test an animal on a sequence task, a single cell might spike for a butterfly if it appears first, but spike for a padlock if it appears second. Its behavior is highly context-dependent. This means the cortex is an overlapping web of multifunctional networks that change their membership in milliseconds. If the brain operated solely on static, point-to-point connections, managing this level of flexibility would require the sub-second rewiring of trillions of synapses on the fly. Computationally, that is completely intractable. It would cause a biological system to burn out instantly. The brain needed a shortcut, and evolution found one in basic electromagnetism. Every time a neuron fires, it creates a tiny ripple in the local electric field. When millions of them fire together, those ripples construct macro-scale electric fields, brainwaves. For decades, mainstream neuroscience dismissed brainwaves as an epiphenomenon, meaningless noise like the hum of a car engine. But Dr. Miller argues that brainwaves are not the hum of the engine. They are the steering wheel. This is the core of spatial computing. Think of bottom-up sensory information as raw spray paint, rising up through the superficial layers of your cortex as high-frequency gamma waves, above 30 Hz. To prevent you from going insane from sensory overload, your frontal lobe, the executive center, sends down slow to mid-frequency, alpha and beta waves between 10 and 25 Hz. These top-down waves act like moving stencils. They physically inhibit specific regions of the cortex, dynamically carving out pathways where the sensory spray paint is allowed to express itself. By shifting these stencils across the physical space of the cortex, the brain changes its program in a fraction of a second, without having to change a single physical connection. When we record hundreds of neurons simultaneously, their individual spikes look chaotic. But mathematically, if you plot them in a high-dimensional space, their collective behavior collapses into a highly organized, low-dimensional trajectory. They move together like a murmuration of birds. And what guides this flock? Traveling waves that literally rotate and sweep across the physical geometry of your brain. This is continuous, analog computation. Unlike a digital computer, which must painstakingly break down the continuous world into ones and zeros, the physics of waves allows the brain to calculate complex differential equations in parallel, instantly, through wave-wave interference. When you look at general anesthesia, this becomes crystal clear. Anesthetics like Propofol and Ketamine target entirely different molecular pathways, yet they all produce the exact same macro signature. They destroy high-frequency cognitive chatter, lock the brain into a slow delta wave below 1 Hz, and shift wave phases 110 degrees out of alignment. By misaligning the waves, anesthesia literally fragments the communication space of the cortex. The analog computer is forced offline. This leads to a profound conclusion about the nature of mind. If we want to build true, energy-efficient intelligence, connectionism and digital brute force might only take us so far. Deep learning is a great way to store information, but manipulating it dynamically requires the physics of fields. Consciousness isn't a digital program running on biological hardware. It is a macro-scale wave pattern, broad and organized enough to bind the physical layers of the cortex into a single, unified, self-governing ensemble. The mind isn't wired, it is tuned. If you want to dive deeper into the fractal layers of biology, computation, and the emergence of consciousness, hit subscribe. Until next time, stay curious.